Well, thank you, Kieran, and welcome to the actual talk. Sorry about the little technical issues, including my own with my own camera, but there we are. Some of you may know that I've been working at Bristol Museum now for quite a long time. I've just retired, but during that time here in Bristol, we've had the fantastic opportunity to work with the University of Bristol. And it's been a wonderful time to exploit and use our natural history collections, and in particular our Lepidoptera collections, and to work in collaboration with Professor Marc Holderied, who's going to give our talk tonight, and has been investigating the Lepidoptera and the moths, which you'd think are perhaps the most well-known group of insects in the whole world. But what is absolutely stunning is the new information that is being discovered and found about their behavior, their morphology, and the structures, and how they interact in the wild with their predators in this case. So it's been a great pleasure to invite Marc to come along and talk to this excellent audience tonight about his recent research and his team. And please, I'm sure you'll fully enjoy this. So over to you, Marc. Off you go. Thank you.
Okay, well, thank you so much for inviting me, Ray and team. It's a great pleasure to be here and speaking to you. I just realized that this is my biggest ever online audience, so I'll try not to be too nervous about that. So welcome, everybody. Thanks for the nice introduction, Ray. So I will be talking about wingtip decoys and stealth cloaks, but an advance warning, rather than 2 stories, you get 2 extra stories, so 2 for free. And there is 2 reasons for that. The first one is just something I could not talk about because it has some relation to our hosts tonight. And then the other one, because it has to do with David Agassiz, who I've seen in the audience, and it covers some story that we have been working on over the past years. By doing so, and by talking about my first subject, I'm breaking 2 of my principles of online speaking. The first one is never talk about stuff that's unpublished. So you'll get a world first of unpublished data at the start of this. And the second is to talk about moths, because that first story is not about moths at all, as you'll see. So this is setting the stage for what this all is about. I'm a bioacoustician. I'm interested in biosonar and how bats use biosonar to find insects, and how insects play all sorts of tricks to avoid being a bat's next meal. And my first story is this one. So here you've got the logo of the British Entomological and Natural History Society. And I've always ID'd this as a nematopteran. In my field, that is the Dielocrocia hebraea that I study in the Middle East. I hope that I haven't got that wrong. But when I applied for a sabbatical a few years ago, I shamelessly used that logo to justify definitely having to study these tiny creatures, which have the most amazing ecology. And I'll only talk about one tiny bit of their ecology right now. So this is a low quality, apologies for that, video slowed down version of their little display flight. So when you see them in the natural habitat, they aggregate in groups. They're about the size of a mosquito in body length, a bit bigger. And they have these weird swinging, undulating motions, and they swing these modified hind wings back and forth. And if you watch them do this close to walls, I think this is a mechanism how they keep distance to the walls, because they push themselves away from the wall with their hind wings. It's also a mechanism to keep distance from the floor, because when they get too low, then they would just brush and push themselves off the ground. And keep in mind that these guys live in caves, so it might be very dark in there. And one reason why they don't want to get in touch with the ground is this. These are their larvae, they're highly predatory, and they have a pretty high vertical reach. So I think there might be a correlation between the length of these hind wings and the reach of the larvae trying to grab anything they can eat. And they are known to be cannibalistic. That's one of my pet theories that I have to test. Well, when they're flying at night, in particular in caves, they share this space, of course, with my favorite study animal, and that's the bat. and the bats would have no problem in accepting these onto their diet. So we did a little experiment and we played some sound, and you could see them. It was over in an instant. So you can see them fly, and then you hear a high peep, and this is when I produce some ultrasound, and they immediately land. Now, this is the world first. Nobody knew about this, and I've not talked about this ever, but as a means of giving back to the BNHS for sharing their logo, this is what they do. So they respond to ultrasound by stopping flight. So I did behavioral experiments, and you can see that it actually has to be rather high intensity ultrasound for this to work. But if you translate that into over what distance, they would respond by stopping to fly. You can see that a bat would be, a searching bat would be about 2 meters away, and that would be at all the frequencies that bats use. 15 kilohertz is too low. No bat that would use 15 kilohertz or below 20 kilohertz would ever attack such a small insect. So it looks as if their behavior is there to make them get out of harm's way. Unpublished and exciting. So now over to the stories that I actually promised to talk about. This is a picture taken in the Middle East of a fruit orchard that is heavily infested by whatever produced these, well, which look like spider webs. And of course, with the people, the audience we have here today, most people will have spotted that this is not spiders, but these are the webs of large aggregations of caterpillars. And in this particular case, it's this species here. So it's a species of Hyponomuta. You can see it's a microlepidopteran. It's about, well, 1.5 centimeters long, and it has this beautiful white with black spots, aposematic warning color. And they, of course, occur in massive numbers around their communal roosts when they're taking flight. And they're flying, they're active at night as well. So that means they would also be a preferred prey item for bats. And the question is, do they have any defenses against these bats? The aposematic coloration, which indicates that they're distasteful, they are full of chemicals that birds have been shown to dislike. I tried a freshly killed one, and it's really bitter, so it is an unpleasant experience. So we wanted to see whether somehow they signal their distastefulness to their batty predators. And that's what we found. So I hope you can hear the noises that this flapping insect is making. This is at a different rate of slowing down. So you can hear trains of clicks whenever the wing is tilted. This is something that nobody knew, but David Agassiz suspected when he found a specific structure in the hindwing, which we'll see on the next slide. So these guys produce ultrasound. They produce this ultrasound in a clear window at the base of their hindwing. It's that structure here. If you look at a close-up, you can see that there is some interesting modifications. There's some normal scales. Here there's a clear area, which we call the window. And then you've got a striped, striated area, which actually is a series of troughs and ridges. And this structure somehow produces the sound. And what happens is that during the bending of the wing, the fold line, which runs along here, that's one of the major fold lines in the wing, creates a rotation along this longitudinal axis, and it makes each of these whitish lines, each of these striations buckle through. And as they buckle through, each of them produces a click, and they buckle through in this direction on the upward and in this direction on the downward. And that creates these series of clicks. So the number of clicks and the number of striation match. Then Liam O'Reilly, who was the PhD student working on this, did a systematic scan for clear patches in loads of Microlepidoptera. And interestingly, he found clear patches not only where Hyponomuta has it in the hindwing with this red fold line, but other examples in the forewing. We found 3 different regions in the forewing that have such clear patches. Now, a clear patch is no proof of sound production, and we didn't get a hold of all the animals. But in the last slide of this section, you'll see that actually we found sound production examples for all 4 of these regions. So because they're operated by the flexion of the wing, we call these guys an aeroelastic or wing beat powered timble, timble being a sound producing mechanism used by an insect. So that was interesting. We published that 2 years in Frontiers in Ecology and Evolution. And here in this audience, I can probably get away with a few phylogenetic trees. Here you can see the superfamilies. And in most of the Microlepidopteran superfamilies, we have some examples of such sound production. And let me draw your attention to this group here, in particular the Saturniidae. They have 3 different genera in there. And each of these genera produces the sound at a different region in the forewing, which is remarkable diversity within one group. And you can see that the hindwing one, the green one, is fairly common, and it might have evolved a number of times independently. In some groups, it is very common to see this type of sound production. In others, it's rarer. But it seems to be an incredibly powerful and successful strategy to produce these sounds. And I should say, before David pointed us in this direction, nobody had any clue that this was actually happening. So what is the use? What's the meaning? Why do they produce this? And we can learn a lot about the function of this by comparing it to a very well-known defense mechanism in moths, and that's in the tiger moth. So here I've got an example of the genus Cycnia, and they produce aposematic signaling sounds. Some species are believed to even produce sonar jamming sounds in the ultrasonic frequency range that either warn the bat of their distastefulness or jam them or startle them. And these guys do it with this structure here. That's a standard thoracic timbre. That's a thinned out area at their thorax, at the mid body part. There's a muscle attached to the inside and it buckles in. And now if you compare this structure to the aeroelastic wing timbre, you can see a lot of analogies. So you can see this clear area here, the window, and you can see the striated band right next to it. And that means that on the wing and on the body, evolution has twice invented that type of sound production, powered by a completely different mechanism. So it's a beautiful example of convergent evolution. Now let me play you the sound. This is one from Cycnia and the other from Hyponemuta. So the first one was the tiger moth, the second was the Hyponemuta. Now Hyponemuta always has this sound on. So whenever they fly, they produce these sounds. While Cycnia is a bit smarter and only produces the sound when a bat is in approach. But both of them are what we would call acoustic mimics of each other because their sound are very similar. And many examples that do this type of signaling have similar sound patterns, both temporally and spectrally, and also in amplitude. Now, you might ask, if you're a flying insect and you're giving away your presence by producing sound all the time, isn't that going to increase the risk of you being found by a passing by bat? And that is indeed the case. It would be doing that. But we measured here how loud these clicks are and over what distance a bat would hear them. And then we related that to the echo strength of the intact insect in flight. And as you can see is that the wing clicks are pretty much following the lines set out by the echo intensity. So that means the clicks make them only marginally more detectable than their echo would give away their presence anyway. So it's a beautiful system. It's a warning signal that only kicks in when you are detected already. And because both Cycnia and Hyponemuta and the other examples are all chemically defended, we call this a case of acoustic Müllerian mimicry. Very cool story that nobody knew about until a few years ago. If there's any moth enthusiasts out there that do moth trapping, we are very keen to get more recordings of more species of microlabs So many people that like moths also have a bat detector. So I encourage you all to take a bat detector to your moth trap and listen to your moths as they fly past. And if you can take a recording of that, that would be super useful. I'd be happy to hear from you. Okay, now to one of the stories that I actually promised to do, and that is concerning one of the largest moths on the planet, the Atlas moth, Atticus atlas. It's not the largest, it's one of the largest, find it in Asia. It's a tropical species, and it's very popular with moth breeders, so you can get them from the livestock trade. And they have this really exceptional wing shape, with the forewing being elongated into this lobe, which has a really weird patterning. And if you read the literature on camouflage, people have claimed that this looks a bit like a head of a snake. I think there is some resemblance, and if you include the whole fringe area of the wing, you could even imagine that these might be ventral scales on a snake body, and that's the back with some counter shading. So yeah, people might argue that that's good enough to fool a bird. But is it good enough to fool some image classification algorithms? So what I did is a Bing image search just of this region and see what Bing, which is just an artificial intelligence trained on all the photos out there in the internet, what they think. And lo and behold, Bing thinks that these are maybe not snakes, but lizards. So it looks like this pattern here has enough features of a lizard to trigger some classifiers. And a bird's brain is nothing else than a classifier. So here we go. And by the way, you'll see that my slider here is down. So the first hits that Bing brought in their defense weren't snakes or lizards. The first hits were indeed the right matches of these wings. But that should be good enough to startle or delay a bird's attack to this moth. So if you look at these weird wing shapes, and now we are talking exclusively about Saturniidae moths, silkmoths, giant silkmoths, you can see that these deformed wings, these lobes at the forewing tip, are quite common. And I don't know whether everybody can spot that, but they have one anatomical feature in common. And I'm not going to ask what it is, I'm going to tell you. So if you look here, you can see that that looks like there is a region of the wing that isn't fully extended. There's a bit too much wing membrane between the wings. And you can see that in all the examples I've chosen here. So they've got this in common. Now, looking at some of the other defenses that Saturniids are known for, we wanted to investigate whether this has something to do with defending themselves against bat echolocation. In particular, we're going to propose that this is a so-called decoy, where you've got a sonar, or in this case, radar-guided missile that attacks, replace that with a bat, and you've got your real target, which is this fighter plane, and you've got your fake target, which is this towed decoy. And the idea is that these ripples at the wingtips might be acting as decoys. And in that, they would be doing something that has been known for a few years now from Saturniids that have long hindwing extensions. We've got these long streamers that are folded, and bats like to attack these, which means this body part might be lost or damaged, but the body is unaffected. So we are proposing that some moths that are known to do this with the hindwing are now joined with a similar defense mechanism by these lobed forewings. And here you can see how well rippled this structure is. I also want to point out these regions here, which are what we call folds, and you will understand their significance in a second as well. So what we did is we used an apparatus that allows us to measure the echoes that come from certain body parts. I'll show you some examples of how exactly we do this in a second. But what we can do is we can calculate something that's called target strength difference. And what we are calculating the difference for is between the body and these wings, wingtips. And a difference in negative numbers means that the body is louder. And the positive number means that the decoy is louder. And if you now look at our example species, you can see that the loudest echo for these three with the lobes, and these guys have both lobes and ripples and folds in pretty much all frequencies bar the lowest. The decoy is by far the strongest echo. And that is the decoy wind proportion. So we measure that for all the different directions that a bat might attack from. And bats will attack the streamers, if they go for the loudest echo, between 60 and 90% of the time when they are using such high frequencies. So that's a pretty remarkable acoustic performance. These guys, a middle group, have ripples but no folds. Still, they have a 50-50 win ratio. Some of them not that good. But if you are unmodified, like these smaller Saturniids, you can see that the body always wins. So the difference between 20% of the attacks to the decoy and 80% to the body, or up to 90% to the decoy, is a difference that makes the difference of life and death. Now, comparing this to the established example of Actias luna, where we know that bats attack these, you can see that the Actias luna, that's the relevant line here for the hindwing, that's only a 50-50 chance for an attack on the body compared to this analysis. So that means the actual experts in decoys are not the Actias luna, it's the Atticus atlas, which is a much more functional, much more effective decoy in their wing. We did some structural analysis and looked at how this works. So in these folded regions, there are many surfaces going in different directions. So if we do a directional analysis, we can see that there is a lot more directions covered. So that's a whole sphere plotted in 2D here. So there's lots of region, up to 51% has more than 2% of the area dedicated to that particular direction, compared to a normal wing where there's only a tiny little region in which there would be a surface that points in that direction. So we already structurally, that wing, that rippled wing, is more omnidirectional. That's pretty intuitive, but there's more to this structure. If you look at these wings, and now we can see a combined image of half a Atticus atlas, and on this side is what we call an acoustic image. So I've developed a little apparatus called an acoustic tomograph. I'll show you a schematic of one in a second, where we can take many different echoes, the same way a bat would, and then combine that using maths that are also used in medical imaging, for example, in ultrasound imaging of unborn babies. And we use that same math to create these acoustic images. And what you can see in color coding is that the body barely has any echo, very little echo coming off the wing, maybe here where the fore and the hind wing overlap. But then here, the rippled region is where all the echo energy is coming from. So a bat looking for a target would definitely attack that region, while the body would be a very uninteresting target for a sonar-guided one, predator. And the question is, how does this work? And it's all in this ripple structure. And the important bit is that it's a retroreflector which operates with multiple reflections. So this is a cross-section down here through this undulating region of ripples, and you can fit spheres in here. So these regions from the top and then the alternating regions from below mean that if sound hits here the sidewall and it hits it at the right angle, it will be reflected, let's say, by 45 degrees. Then it hits the other wall, which is symmetrical, and also adds 45 degrees. That's, oh, sorry, not 45, 90 degree, 90 and 90. That's 180 degrees. So sound is sent back in exactly the direction that it's coming from. These hemispheric retroreflectors are a common principle that's used by engineers, but it's also used by other organisms already. So these ripples are hemispherical retroreflectors, and you can even see the individual hemispheres in that false color image. But that's not all. I've mentioned these folds. Cross-section along this red line shows that there are strong angles here. if you do the analysis, a lot of these are 90-degree angles. And in analogy to these hemispherical retroreflectors, we've got corner retroreflectors here, sound coming in, being reflected at 90-degree, hitting the opposite wall, again reflected by 90-degree and sending the sound back. And this is the trick that really makes these wing regions such extraordinary reflectors. Any deviation from 90-degree in these folds, or from being perfect hemispheres in the hemispheric retroreflectors, would defeat the purpose. So small changes make a big difference. So if you want this to work, it really has to have these specific angles, and it does. And this is just to remind you, if you don't have any decoys, your body always is the loudest echo, so you always lose. If you have a hindwing decoy, it's a 50-50 chance, but if you've got a forewing decoy, and these are averages, you will win in so many cases and protect your body. You've just gained an extra life. And here's some direct imaging evidence. This is a modified acoustic camera where we basically, this is a cockpit view of an echolocating bat. And you can see that here from this wingtip, this is where all the echo energy is coming from. All the rest is much fainter and the body doesn't have an echo at all. This wing is out of the sonar beam, I believe, or it's at the wrong angle, but you can clearly see that even with direct imaging, you can get evidence for these decoys working. I've mentioned that decoys can happen in forewings and in hindwings. So we did a phylogenetic analysis of all the Saturniidae we could get a hold of. And that's the result that we have. You can see in green, these are the ones that have hindwings. This is what others have investigated also behaviorally. But you can also see the blue and red, which are either only ripples or folds and ripples. And you can see that this is a rich pattern. So these things have been found and lost in a number of incidents. There is an interesting region here in the Atticus, and then you can see down here, there's also some that switched from forewing to hindwing reflectors. But the important thing to notice that every species only ever has one decoy, either in the forewing or in the hindwing. So this suggests that one is enough and that there might be cost to having and maintaining both sets of decoys. And now that I've told you that rule, I immediately have one species that breaks that rule, and that's the Hercules moth, which actually is known as the largest moth. There we can see forewing and hindwing decoys in the same species, but in different sexes. So males do one decoy and females do another. So a rich pattern of unknown and unexpected acoustic defenses in these Saturniidae. Okay, and now I'm going to talk about our main research for the last few years, and that has to do with acoustic camouflage. In this case, acoustic stealth camouflage. So if you're looking at this beautiful silk moth here, I think it's a Chinese cabbage moth. It has loads of interesting features to it. And one thing that many of us associate with moths is that they're furrier than butterflies. So if you look at this central part here on the body, yes, indeed, there is a lot of furriness to be spotted in that region. So if you are looking at these organisms not with your eyes, but with your bat goggles on, so what the echo of this structure look like, then fur might actually be having some sound absorptive properties and reduce the echo that's coming back. So that's what we tried to find out. We used our tomograph. Here's the schematic I promised. We've got our insect in the center. We've got one turntable here, another turntable operating this arm, and this is our artificial bat. And then we get acoustic images like this one. That's the same image, but on a dB scale, which is more fitting to what a mammalian hearing would do. And what you can see here is that this organism intact has most of the echoes coming off the wingtip. There's a bit of a mounting artifact because you never see the wings in that way. So the hindwing region is always problematic because in flight it's flat, but when they're mounted, they are at angles, and angles produce echoes. So ignore these, most echoes from the wingtip. So that's another wingtip decoy species. But what we did is I had an expert moth shaver. I still say he's the world expert in shaving moths. So he removed all the fur on the body and only the body and left all the rest unmodified. And then we took the same image again, and you can see how now the body lights up and is by far the loudest. So we tried to do this a bit more systematically, and we quantified the effect of the body fur for 2 moths and 2 butterflies. And what we found is that the presence of the fur makes a big difference to the echo strength. That's the target strength. Red is the strength of the echo without fur. Yellow is the strength of the echo with fur. And down here, you can see that translates that difference between the 2 states into a change in the detectability. You can read this axis as the predation risk. So the presence of fur reduces the risk of being detected across all frequencies that bats are using by about 40%. And that's a massive gain. Just a 2.5 millimeter layer of fur on the body gives you a fantastic protection. This species is similar, but not just as good, but still above 30% protection for most of the frequencies. If you look at the butterflies, no such thing. In some cases, the presence of the fur actually makes them more reflective rather than less reflective. So clearly evolution has shaped this fur. What's the mechanism behind? If you look at some close-up images, you can see that the fur on moths indeed is longer and denser. Here, that's the insertion point density on the back of a moth and on the back of 2 butterflies. And you can see you couldn't fit another hair on the back of this moth. Similarly in this one, but in the butterflies, there's a lot of space. They just don't use the space as efficiently as the moths do. So how does this work? This, by the way, is not a face of a scary clown. This is a false color scan of a moth thorax cut in half, and you can see the different tufts of hair, highly complex architecture. By the way, you've got the tegulae here. These are little flaps that cover the wing joints, and they on their upper surface carry the fur. Why do we think they have these tegulae? These are necessary because you can't have fur on your wing joint. But if your wing joint is exposed, it produces a strong echo. So these tegulae fold back over the wing joint and carry a layer of fur that doesn't hamper the free motion of the wing joint. And if we then look at the thickness of the scale of the hair fur layer, you can see that it's several millimeters long and it has a very high porosity. So there's only like 4% of matter and the rest is air. And if you look closer, a single hair is porous in itself. We talk about nanoporosity. So this is a couple of micrometers thick, and you can see that there is this trabecular porous structure inside. Now, what does that tell us about the sound absorption properties? Well, first of all, fibrous sound absorbers, like the hairs ordered in this structure here, are known and are used by humans in fibrous sound absorbers, like this example down here, which I believe is hemp. And you also have got cellular sound absorbers of this type, which have these nanocellular structure. In both cases, the sound enters the spaces within the structure and then is absorbed into heat and translated into heat by friction in these confined spaces. So there is a lot of theory around there, and we've looked at how good the moth absorber is with respect to technical absorbers using the same technology or the same approach. And it turns out that moths are as good as we are, not better, maybe slightly better at low frequencies, but there is no dramatic difference in how good they are. And the rule of thumb that applies to both, to the moth fur and to the technical absorbers, is you want to be at about 1/10 of the wavelength of the sound that you want to absorb. If you're thinner, you can't absorb it anymore. And remember this 1/10 of the wavelength, because that's going to be important for when we're talking about the other bits. So back to our moth here. We now know that the fur absorbs the sound. Now, if you want to stay hidden from a bat sonar, of course, you need to protect every body part, not just the body. So how about the wings? Don't wings produce echo? When we measure the wings, indeed, they do produce echoes. But if you want to reduce their echo reflection, you can't just put fur on them. Think about a moth wing that has 2.5 millimeters of fur on both surfaces. That would not be aerodynamically possible. And they don't have that. So how do they avoid being detected by their wing echoes? And if they don't care about their wing echoes, why do they have the whole mumbo jumbo of the fur in the first place? So you want to have a comprehensive coverage, but the structure on the wing is much thinner than the structure on the body. So what's going on here? Let's have a closer look at what these wings look like. So on the wings, you've got these tiny scales, which are the same structures as the hair, but just grown into a different shape. And these tiny structures, these scales, look a bit like hands. They have a stalk that is inserted into the membrane, and they've got a palm, and they've got fingers that are stretched out, and they overlap and produce very complex architectures. That's just one example. Wherever you look on a moth wing, you'll find a different type of scale and a different type of tiling pattern. So we went straight in and measured the moth scale sound absorbing properties. And again, we compared moths in orange to butterflies in blue. You can see the structural differences in these inserts here, very different architectures. And now this is the key figure of this part of the talk. So here we've plotted wing thickness over the wavelengths. You can leave this as frequency, low frequencies on the left, high frequencies on the right. And all the blue curves are butterflies, and they all have negative values. And that value is called a relative absorption coefficient. That means how much of the impinging energy is absorbed. Now, if you're going to 0, that means there is no effect. If you're going to 1, that means that all the sound energy is absorbed. If you're going to -1, that means you have just doubled the reflection. So it's a lot more energy that comes back as an effect of the presence of the scales. So this plot here shows us the acoustic effect of the scales. The scales on a butterfly wing make the echoes much louder, while the scales on a moth wing make the echoes much fainter. And the relevant or intriguing thing is that these curves have their highest values on the left, which is at the lowest frequency. So if we, for example, go for this curve, it reaches over 70% of sound absorption, and that's the energy absorbed at low frequencies. It might have a plateau here, it might carry on to lower frequencies, but that's the lowest frequencies we measure. And that is something that's remarkable. So we've got a structure that has a high absorption over many different wavelengths. And now I want to draw your attention to the axis down here. This is the 1/10 threshold, the wall that we can't exceed or surpass in a normal sound absorber. But these moths, they go down to 1/100. So they achieve the same acoustic performance at 1/10 of the thickness. And that means that what we have is a scale layer on a wing that is a deep subwavelength and also broadband sound absorber. And that is, to put it bluntly, that's the holy grail of sound absorber technology. Everybody wants that, and moths have found it, but we don't know how. So we spent the last 5-6 years trying to understand exactly how this works. And for that, we did some fancy structural analysis. So here you can see an individual scale that we've scanned. And if we look very closely, you can see that the scale itself consists of ridges with lots of holes in it. So that's just a zoom through the different layers of scales. And everything happens well below a millimeter. And everything here is in the micrometer range. So these are tiny, tiny structures. And of course, this is the stuff that comes off the wing of a moth or a butterfly when you touch them. They're dead tissue, they're just chitin. And just stick into another equally dead bit of membrane on the wing. So this one scale that I've just shown you is the best studied scale on the planet. We've taken this scale and put it in an apparatus that can measure its vibrations, and then we sent sound at it. So we measured how it responds to the presence of sound and the ultrasonic frequency range, and these are frequencies that bats are using. So if we do this, we found that this particular scale had a particular rotation mode. It's like when you wave somebody with your hand going up and down at 26 or 27 kilohertz. It was like a shaking your hand, rotating it along your arm axis at 90 kilohertz. And then a third one, which is if you're waving your hand from the left to the right. So these are three modes that we found in our laser Doppler scanning measurements. When we then try to model that exact same scale by replicating and homogenizing the structure, the nanostructure of the scales, we found the exact same three resonance modes at pretty much the same frequencies. The first and the third modes are exactly the same. The middle one is slightly different, but it's harder to measure. And what does that mean? If the scale vibrates, that means that the acoustic energy in the sound is not reflected, but turned into mechanical energy in the scale motion. That means at 27.6 kilohertz, this scale absorbs sound, and it does again at 90 and again at 150. So that means it offers partial protection against echo generation. Now, just absorbing three frequencies won't do the trick, and this is where this fantastic diversity of scales comes into play. So you might remember that on the butterfly wings, the scales looked all very similar, like roof tiles. But here we can see different classes of scales, and every class has a huge diversity of anatomies and morphologies. And each of them could possibly mean that they're tuned to different frequencies. So we used our laser scanner again and scanned a whole region of a moth wing or a butterfly wing and looked for resonances, which indicate that at this frequency, the sound absorber is functioning. And these bars here show us that we found the resonances across all the frequencies that bats use with an equal number of resonances in the moth wing. And we looked at the sizes and shapes of these moth scales and calculated where they should resonate. And this is the box plots up there. You can see that all the different frequencies can be generated by the anatomy of the scales. So moth's diversity of scales really makes sure that all the frequencies are absorbed. While on a butterfly, because their scales are so similar, you can see that most of them would absorb at the same frequency or resonate at the same frequency. And that's exactly what we find in these two examples. Some of them, longer hairs that are rarer, also play a role and resonate at higher frequencies. So yet another beautiful example of how evolution has tuned these scales to do what the moth needs, and that's protection against bats and against all the frequencies that bats use. Now, this is not trivial, because if you've got a single resonator that absorbs one frequency, and you have to absorb, say, 100 kilohertz, that means that this tiny region on the wing absorbs this frequency, but the next region to absorb that frequency might be far away. And that's not what we see. What we see is that the whole wing absorbs all frequencies. And this is where something very exotic comes into play. What we discovered is that the scales, when you put them together, and this is just a mathematical calculation to prove that concept, they interact with each other, and they interact in a manner that is formally unknown. Put it in different words, if you put all the units on themselves, just one of these scales, they produce a certain absorption. That would be, for example, at 45 kilohertz, that pinkish curve here. And if you change the scale geometry, then you can see that that frequency can change over that frequency range, but the shape always stays the same. Now, if we take the same number of scales and put them together, you get this black absorption curve. So the area under this black curve is much bigger than the area of any of the other curves. And the peak is even higher than the highest peak in the single curves. So that means by putting all these different resonators together, you're getting something that's called an emergent property. The sum of this structure is bigger. So the total of that structure is a bigger performance, a stronger absorption than the sum of their individual contributions. And that is the definition of a metamaterial. Metamaterials are structures that are using unit cells, individual things, in this case scales, put them in a specific arrangement, and then you get these exotic emergent properties. So this turns the moth wings into a really powerful sound absorber metamaterial. So to summarize, the fur on the body is a porous absorber. The scales on the wings are deep subwavelength broadband absorbers, and they're achieving this by being an acoustic metamaterials with scales at unit cells, and they're ultra thin because they resonate, because they move, and this allows these moths to be broadband by what we call a tuned array. And this really is some very advanced physics that evolution has discovered here. But then I always say evolution doesn't care how complicated the math is. It will play around until it has found a solution that works. But it doesn't make it easy for us as engineers trying to retrofit what is going on here. And we want to retrofit it because moths are 10 times better than what we can do. So the promise of the Mothwing is, if we can get something that is 10 times thinner than our current sound absorbers for our offices and homes, we might actually have a real win in terms of the size, the thickness, the mass, the volume that we need to dedicate in our rooms to get nice soundscapes and noise-free environments. So in other words, I want to learn from the Mothwing to design acoustic wallpaper that is much thinner, ideally 10 times thinner than what we currently have. First, we needed to show that Mothwings can work against a background. So if you want to use wallpaper, there's a wall behind the wallpaper. So we used our apparatus to put little samples of Mothwing on a metal disc, and then we compared the acoustic effect. And in short, we can see that if we've got an intact wing or a partly shaven wing, it always reflects far less it works. So we can use the principle to reduce sound reflection from a wall, and that's what we can work with. Here we can see that this is also omnidirectional, so it works for many different directions of sound incidence. Knowing this, we have taken to prototyping, to trying to build an artificial Mothwing sound absorber. And one of the tricks we used is direct write lithography. So these are scaled up versions of scales, such that they resonate not in the ultrasound, but at frequencies that we as humans can hear. That's of course one design challenge. Translate the ultrasound mechanism into audible frequencies. And here is our latest. So these are some prototypes that we test in this apparatus here. And our current absorber has a thickness of 20 millimeter. It has a thickness to wavelength ratio to 1/30. So it's only a third of the thickness that current sound absorbers produce. We've got some that work better, up to 1/45. And the absorption coefficient of this particular one is more than 80% of the energy. You can see that it achieves this over well over 1 octave. So we have managed to get audible frequency range. I should have said that this here, I believe, is 400 hertz, and this here is 900 hertz or 1000 hertz. So we really have achieved what we wanted to. At the moment, our bandwidth is limited to 1 octave, but that's mainly due to the size of our prototypes. We can only fit a certain number of different scales on there. If you want to get broader bandwidth, we need more different scales. So we are building a new and bigger testing suite at the moment. So I've got some EPSRC funding to build 7 square meters of sonic wallpaper, which should be ready and tested by Easter this year. So the idea is that at some point, people might be able to put sonic wallpaper in their living room and just keep out the road noise. And keep in mind that traffic noise is the second highest environmental health risk in the Western world. And the British government estimates that the damage, the cost in England alone of road noise alone is about 9 billion per year. And that's about the same cost of all road accidents taken together. So if we can reduce our noisy environment, we are doing something for our health and we're doing something for our economy. And that's what we are setting out to do. And who would have thought that the furry and well-studied moths have such amazing discoveries in keeping for us to discover. That's the end of my talk. These are just a few people who have helped. This is mainly the team that has helped with the sonar prototyping, but I've mentioned some other contributors throughout the talk. Thank you for your attention.
Thank you, Marc, for a fascinating talk. That was really, really great. We've got loads of questions coming in the chat. So I'm going to start though with questions. Yeah, I'm going to start with questions from the chat. If anybody has a question that they'd like to ask in person, if they could raise their hand, and we'll come to you one by one. But Anka, if I come to you first, have we got? What are the burning questions from the chat?
Yeah. Well, we've got actually quite a few. And if there are any more coming through now, I'm probably going to miss them. So I'm just going to start from the top. So they're quite varied, but they kind of started as you went through your presentation. So the first one comes from another Marc, who says, fantastic presentation. Is there any indication of how the moth wing modifications that produce the ultrasound could have occurred? For example, are they modifications of a certain part of the wing structure?
Yeah, that's a good question. So how do we link this function to the anatomy? So the scales were there before the bats were there. We know this from fossil record. So I think the original function of these scales is probably other predator protection against spider webs, so they're anti-stick protection. They're also slippery, so if an insect is grabbed by a predator, they can slide out. We've all experienced that, how difficult it is. That's all in the nanostructure of these scales, and they don't even have to break off to do this. We are looking at how these scales help in protecting the mothwing from impact by rain and hail, so there's a function there as well. So the interesting thing is that there is this structure, and each of these scales is produced by the cytoskeleton of a single cell. So a single cell in the development of this wing produces this scale. So some of these cells are several millimeters long, which is amazing in itself. And evolution has found this cytoskeleton to chitin structure production line and a very productive playground for doing exciting things. So we found that they are using it for sound absorption, but we are all familiar with these very shiny metallic structural colors, for example, of the morpho butterfly and many other species. And they're also created by the nanostructure in the wing. And I've told you about the moth sound absorber being a metamaterial, and it's the only and first metamaterial sound absorber found in nature. These blue metallic colors are another type of metamaterial. They're photonic metamaterials. So the two most important metamaterials we have found in nature have been developed by scales on Lepidopteran wings. So it always amazes me to see how, if you give evolution a playground that is very versatile, like the cytoskeleton in an intracellular production line, it manages to achieve remarkable things. I hope that answers that question.
Yeah, thanks very much, Marc. I'm going to come back to Anka. We're going to keep coming back to you, Anka, I'm afraid, because you've raised your hand yet. Just to let people know, you're welcome to turn your videos on now as well, if you don't mind showing up in the recording. I'm not able to edit people out of the recording, so you will appear. That's a friendly warning, but yeah, we can, now we're not presenting, people can turn on their videos if they would like to. Right, Anka, what's our next question?
Right, so the next question is from Niels, and this was actually when you were discussing the large atlas moths, and he was wondering what kind of bats would forage on these moths. They're very large, and very large bats in Southeast Asia are either frugivorous or glean insects on the ground or on the foliage, often without echolocation.
So that's a really good question, and there's this theory that size matters. So if you're too big prey item, then you're not selected for by your predator, and that certainly has been applied to bat species. I think my answer to this question is twofold. First of all, the largest insectivorous bat on the planet is found in Southeast Asia, Cheromelis. So there might be a bat out there that is perfectly capable of attacking these large moths. And the large wing doesn't mean that you're actually such a scary prey item. If you only look at the body, that's much more manageable, even for medium-sized bats like a Scotophilus. So I'm sure there is some predators out there that would still take them. A small to medium-sized bat would probably shy back from attacking them. That's true indeed.
Yeah, Anka, I think we're gonna keep coming to you unless somebody puts their hand up.
Okay, you can just interrupt Marc or myself. So Neil was wondering, are there any UK moths that use these features?
Okay, well, first of all, I'm sure many of you know that we do have Saturniids in this country, the emperor. We've studied it, it does the whole thing. So it has a sound absorber. It even has this little eye spot, but I don't think that the emperor has an acoustic wingtip decoy. And that is, it's a bit too small. The background for this is that a bat has a certain attack radius. And if the whole insect fits into this attack radius, the decoy doesn't work. So the decoy needs to be separated from the body by at least one radius, attack radius. And we always say that's probably 5 centimeters in diameter. And because our emperor fits in that almost, I don't think they have this decoy. But the sound absorbing features, we've tested other families that are abundant in the UK. Yeah, several of them have partial sound absorption or full sound absorption. So it seems to be more common than we would have believed. But the Saturniids are special.
We've got a question from Adrian, Anka. So
Okay.
I'm going to mute you for a second. Oh, Adrian, if you'd like to unmute and ask your question, you're more than welcome to go ahead.
Well, yeah, my question, it's a fascinating talk. I've learned a lot. Have you looked at the difference between nocturnal and diurnal moths? The difference in scale structure is.
Yeah. So that is, of course, one of the first questions we looked at, and it's not as trivial as that, because that's a great control. So if you've got, for example, Uraniates are a really good group because they have diurnal and nocturnal species. And yes, Uraniates have sound absorbing, nocturnal have sound absorbing structures. The problem is that the diurnal ones are very similar in the acoustic properties. So they are not butterflies. So acoustically speaking, they haven't lost that ability. Now we can speculate as to what the reason and the adaptive advantage is, but at the moment I don't have explanation. I could say that we have started to look at the nanostructure, again with David Agassi's help, of the scales of many different moth families. So I think we had managed to get half of the moth families under our SEM. And this nanostructure of the Saturniids is highly absorptive. I didn't even talk about that. But all the moths and butterflies other than Saturniids seem to be very similar to each other. So I think there must be a strong evolutionary signal still inside, where only some of them have gone to the extreme lengths that the Saturniids have gone to.
May I just add supplementary then? Because I mean, the obvious one to look at would be the Micropterigidae, which are the most primitive moths and are all, as far as I know, diurnal. Have you looked at those?
I just yesterday I looked at an SEM scan of the scales of these, and they have some extraordinary features. So they are slightly different to what others are, but mainly by the separation of the longitudinal ridges. You saw those on some of the scans, and they're completely non-porous. They don't have any holes in them. So that if that is the ancestral form, then most of the other taxa have some features that wouldn't make them sound absorbers.
Okay, thank you very much indeed. Thank you.
Thanks for the question, Adrian.
Okay, Anka, we've got no more hands up, so back to you.
Okay, you've kind of touched on this a bit anyway, but Benjamin was asking, is there a correlation between the size of the moth and the likelihood of these decoy wingtips being, or effectiveness of these wingtips?
Yeah. So yeah, I think you sort of asked the right question there. Yes, because of this attack diameter, attack radius that I've mentioned, we only find decoys in really large species. Or some of these Saturniids are small, they're less than 5 centimeter in wingspan, but have extremely long streamers. I'm thinking about something like Eudaimonia, genus Eudaimonia, which I didn't put a picture on there, I should have. But yeah, it's mainly found in really large species.
And Rosie was asking, this is kind of an interesting one, is there any man-made technology that could interfere with the sound defense mechanisms from moths or bat echolocation?
So, I'm just happy that I managed to turn the moth defense into a technological applications. Now you want me to find a trick to defeat it. I don't think something's out there that can do this, but I think it's an intriguing idea. We are actually in our efforts, we are thinking about ways to defeat this mechanism. So in other words, have a wallpaper that can be switched on and off. Well, that is very hush hush and I can't tell anymore.
We won't tell anyone.
So it's a case of you did not hear it here first.
Not going on to YouTube.
You heard nothing. Rosie, would you like to ask your question?
Yeah, thanks. I asked the question about the technology. I suppose it was more from the point of view of the moth, and that is there technology existing that could stop it from using that defense mechanism? So looking at it from the other point of view. Because I'm sure, I don't know, there's something around Wi-Fi that they're not sure if Wi-Fi affects moths and their ability to move about, and yeah, I'm not sure if there is anything, but it was just a question.
Yeah. So if you're interested in sort of interference with non-standard modalities, you mentioned electromagnetic waves there. I think you might want to look at some of the work that my colleague here in Bristol, Daniel Robert, is doing. So he's doing insect electroacoustics, or no, so not electrosensing. So the electric world is completely hidden to us. We don't have a sensor for electric fields, except extremely strong ones, which we then perceive through our mechanoreceptors when our hairs rise, when there's strong static electricity. But insects, he finds, have fantastic dedicated sensor for static electric fields, and they can sense a thunderstorm coming in from a great distance. They can sense whether a flower has recently been visited and is ready to be delivering nectar. So there is an amazing richness of static electric signals out there, that we don't know about. And I think that is probably going in the direction that you are aiming here. So even more exotic interactions.
Thank you. So I'm interested from the conservation side of moths. So, but I don't have any experience in the electromagnetics or any sort of background in physics. So I'd have to, I suppose, if I was going to do any research, I'd have to work in partnership with somebody else. Yeah. Thanks very much.
Thank you, Rosie.
Thank you.
Thanks, Rosie. Right, I think we've got time maybe for 2 more questions. So, Anka, I'm going to come back to you and pick the best 2 out of the chat.
Well, I'm going to pick one which I'm not sure if I'm sure you can answer this, but Priscilla, I think because you earlier were asking moth trappers to try to record these sounds. So Priscilla was asking, what is the best bat sonic equipment?
Okay. So if you're serious about this, you don't just want to have one of these bat detectors that just make the sound audible, but you want one that allows you to record the sound as well. And for that, you need some specialist equipment. Now, there are a couple of solutions out there. NHBS website has all of them, and it will clearly identify which ones are suitable for recording and which ones aren't. I think the cheapest that I know of is the so-called Ultramic that you can connect with a cable to your phone, to your smartphone. It has an Android app. I don't know whether they've got a Mac app yet. And that comes at about 150 pounds, similar for dollars. And there is some other solutions out there that plug into your phone, into your smartphone. And that's what I use when I send people all over the planet to record sounds of insects. And so it's not super cheap, but it is within the range of a very dedicated naturalist. Like the cat, Anke.
She likes moths too. I have one last question from somebody called Ready When You Are. That's the name. Have you looked at other insects with furry wings? For instance, some night-flying Diptera. I guess the flat scales of mosquitoes work like butterflies, so high reflectance.
We haven't. That's a very good question. So the scales on wings, also Lepidoptera, are not the unique taxon to have scales on the wings. I completely agree. The density of scales on the wing is however, highest in Lepidoptera compared to other taxa that have scales on. And that already makes me think that I find some of these Dipteran that I mentioned, for example, less interesting, but I yet have to put a Dipteran scale under my scanner. So yeah, watch this space. There might be some interesting stuff coming as well.
Excellent. Kieran, do we have time for any more, or?
Yeah, we can do one last one.
Let's see. Phil was asking, I'm assuming that there is an evolutionary imperative for bats to counter the acoustic absorption function of wing scales and hairs. Is there any evidence that bats are changing the foraging frequencies?
That is a very cool question. So now we are talking about the predator-prey arms race, where the attacker also wants to improve its attack strategy. And I have to say, it's bad news for the attacker. Once a moth has a functioning stealth cloak that operates at all the bat frequencies, there is very little a bat can do to break through this defense. It really is, when the echo is not generated, it's not there. So you can try whatever you want. The bats have sort of maxed out their hearing ability. So they are, as far as mammals go, they are as sensitive as they can get. They have big ears. At least some of the specialists have really big ears that also interfere with their flight speeds. So there's a bit of a trade-off there. So I cannot even theoretically think of a mechanism how a bat might be able to break through this fantastic stealth cloak.
I'm kind of feeling sorry for the bats.
All right, brilliant. Thank you very much for answering all those questions, Marc, and a fantastic talk.